Okay, this video will go through how to do a transformation using a Casio calculator for general maths. Alright, so this is more aimed at the data sack rather than what you would be required to do in an exam, which I'll do another video on. So a piece of metal is set aside to cool on a day when the temperature in the lab is 28 degrees Celsius. The temperature of the metal is recorded at 2-minute intervals and the results are shown in the table below. So we've got the time in minutes, 2, 4, 6, 8, 10, 12, etc. and the temperature in degrees Celsius. Perform a regression analysis and record R and R squared. So for your SAC, this is really important, especially the R squared, because that is the basis of the improvement of a data transformation. We need to improve R squared, so we need that data first. All right, so if I open up the CAS, I've put my data in statistics. List 1, always put in your EV values. List 2, always put in your RV values. If you do it this way all the time, you won't get confused. Also, with the Casio calculator, don't rename your lists because it's really annoying when you have to reset your graph. If you think that you're going to forget what things are, then by all means relabel them, but I just find it irritating. All right, so doing just a regular linear regression, calc, regression, linear. I haven't changed anything at this point, but I do want my residuals, and I'm always going to put my original residuals in list 3. I go OK, and that is in the right format, and then I'll get my residuals popping out in list 3. This is showing me the graph there. I might even just take a screenshot of that. Now, to get your R and R squared, it was back where we were before, so calc, regression, linear. Okay, so our R squared is pretty good already, so it will be an interesting one to improve, but we want to get that as close to 1. Hopefully you know how to do a regression analysis, because this video is predominantly just looking at transformations. So R squared is 0.93244452. So we need to improve that. All right, so first of all, that's our original graph there. It doesn't look like it's fitting that line very well. However, a test for linearity would be a residual plot. Okay, so a residual plot is a test for linearity. So if I go back to my calculator, I go this one up here, setting the graph. Now with a residual plot, you want whatever you've used for your X list to stay the same. And then wherever you've got your residuals, whatever list that is, whether it's the transform residuals or the actual residuals, that's going to become your Y-axis or your vertical axis. So in this case, the original residuals were in list 3. I go set, and it will come up with the graph. If it doesn't come up with the graph, you just need to click this one here. Okay, so as you can see, we've got a clear pattern. A clear pattern in the residual plot means that a transformation is required in order to linearize it. So at the moment, the regression model that we have got is not a good fit for this data because it's forming a clear pattern. Okay, so a pattern in the residual plot means the original data is not linear. It's not a good model. Okay. So there's a clear pattern in residual plot. So therefore the original data is not linear. Okay, if the original data was linear, we would see a lack of a clear pattern, and that indicates that the least squares regression line was a good fit for that data. All right, so we've determined that we need to do a transformation. Now, picking the transformation is based off your original shape. So see how the data is bending like this. So it's bending like that. What you need to do, this is for the sack, is you need to copy that bend with one of these bends in the circle. Now, what students get a bit confused about is you're only looking at a quadrant at a time, not the whole circle. Okay, so again, looking at this one, it's bending like that. It is matching this quadrant. So in order to linearize that data, we can pick any of those 4 transformations. In the sack, you won't have to do all of them. You would pick however many it says to do in the sack, because it is an analysis task. Like, you do have to look at options and explore different things and see which one's the best option. In an exam, they'll tell you which transformation to do, so it's a bit different. All right, so we could do log y, the reciprocal of y, log x, or the reciprocal of x. Now, you're compressing and you're stretching, etc. I suggest you get your head around transformations before getting too bogged down with that. And then once you've got your head around it, they sort of make sense what you're doing. Okay, so we've been told we're going to do a log transformation to time. So if we go back to the original data, time was our EV value or our X transformation. So we're doing an X transformation. Apply this log transformation and comment on the resulting scatter plot. All right, so I'll go back to my data. Going across, I just want to resize that so I can see the whole thing. So again, we're going to put the same things in our lists over and over and over. List 1, EV. List 2 will be your RV. List 3 will be your original residual values. List 4, you're going to put your transformation, whatever it is. If it's X or Y, we're always going to put it in list 4, always. And then in list 5, we'll always put our new residuals. If you're doing this over and over and over, you will always know where things are. In a sack, when you're doing multiple transformations, just make sure you record your A, B, R, and R squared for your transformations. You do a sketch of your data, like your new scatter plot and your new residual plot, and so then you're writing over the top with each transformation. All right, so we were told we were doing, I've already forgotten, a X transformation, so log X. Down the bottom of list 4 in this calculation cell here, so I just made that go dark, we're going to give the calculator the instruction of logging X. Now, the X list was list 1. So if you bring up your keyboard in the ABC, log base 10, because I'm logging list 1, and then your ABC, and then list 1 no spaces. So this is why I said not to change your list names, because it's really annoying having to write a new thing all the time. If you're just letting it be list 1, list 2, list 3, it's quite easy to remember. Press execute, and all those list 1 values will be logged in list 4. Okay, now we need to perform another analysis of this transform data. So we no longer have our original x data, we now have log of x instead of the x. So again, we do a regression analysis, so calc, regression, linear. Stop at this page. Ask yourself, what did I change? Did I change x or y? In this case, I did a log x transformation. So I'm changing my x list. And where did I put that transformation? I put it in list 4. Now I also want to check that the transformation was successful. How I do that is I do a test for linearity. So I need to run more residuals, my new residuals, which I'm going to put in my next free list, which is list 5, always. I go okay. Now this is important because I need to make sure that my R squared has improved, and if this is for your SAC, you will need the A and B values as well. So I'll just take a little photo of that, and I will put those here so I don't forget them. I'll go back to this. All right, I'll come back to the R squared in a moment, and it's still got my original residual plot, so I need to set my graph. Now at this, I'll just reset it back to a normal EV-RV relationship. So at this point where you're setting the graph, first of all, make sure on is on for draw. Sometimes students will be like, why isn't it drawing? And you've got it on off, so make sure it's on. Now you can set multiple graphs. So if you want to have your flip back and forth to your graphs, you can open up multiple ones and just turn them off if you like. I can never be bothered doing that, but it's totally up to you. You just have to remember to toggle them on and off and remember to do that. So from the original EV versus RV, I've now changed the X to log of X. I put the log of X in list 4, right? I didn't do anything to Y list, so that's changed. That stays the same, okay? I go set, and that's my new graph, my new transform graph. So on just looking at that by eye, I think that is a good improvement of that linearity. It looks like it's fitting that least squares regression line much nicer. I'm just going to take a screenshot of that and put that over here somewhere. Okay, however, that you still need, especially for the SAC, you will still need to do a test for linearity, because your scale might be misleading and it might not be a great fit. We'd have to do a test of linearity. So again, we're going to set our graph. I'll reset this. Oh, actually, no, I'll just leave that as my transform data. So I transform the x-axis. Remember with a residual graph, whatever you use as the x value or in the x list has to be the same. So the x list for both your graph, your original, like your scatter plot, whatever you're looking at, either transform or original, and then your residual of that data has to be the same. So whatever you've got in X list has to be the same. Now, for the residual plot of the transform data, I need my residual values for the transform data on the Y list. which I put in list 5. Okay, now this is all in your summary sheet for the transformations with the wheel and that sort of thing. It's got it all underneath, so you can just follow if you're doing a Y transformation or an X transformation and see what you're putting in what list. But if you do enough of these, it will just be second nature, I promise. So that's our residual plot there. Now, that has definitely got rid of that clear pattern, so that is also an improvement, which is good. So that is a very good transformation. So I'll just chuck that in there. Okay, so that was our new scatter plot. So it went from this guy to this, which is significantly improved in terms of linearity. That least squares regression line fits that data so much better. So much better. And then that's proven by this lack of a clear pattern in this residual plot. Whereas this original data, the residual plot, had this clear pattern. All right? Now, with your SAC data, it is a lot of data and it's raw data. So you may not get a perfect situation where, which is quite different to what you would see with, really small data sets where these have been manipulated to get like a really nice transformation. Whereas in your SAC, we're giving you real data, like real world data. So you may not get a beautiful shift that you may see in an exam question or an exam question like this. All you need to aim to do is do two things. You want to improve your R squared. So that means that you're bringing this closer to 1. So that's the first thing you need to do. And then you need to make sure that your residual plot has improved in terms of getting more of a lack of a clear pattern, right? You could start with something that has a real harsh pattern, and then it is a little bit more skew if it might still sort of resemble some sort of a pattern, but it might have improved, okay? So with a SAC, with raw data, with real big, large sets of data that are numbers from real life, you may not get something that is gone from a absolute pattern like, that. You may get something that's sort of maybe just a little bit changed. That's still an improvement as long as R squared is also improved, all right? But in a SAC as well, you've got to look for your highest R squared, provided that the residual plot has improved. All right. So I'm happy with that because my R squared has improved. The original one was 0.93. And I've gone from 0.93 to 0.998. All right, so that's like 99.8% of the variation in our temperature can be explained by the variation in our log of time. So that's very, very good. All right, so if I write down my A, my B, my R squared, and so 256.22192 and 19566. Now, don't worry if, for example, you originally had so these ones are both negative, but sometimes when you do a transformation, your direction might change. That's totally fine. Sorry, I'm yawning. That's totally fine because when you're doing the predictions for your transformation, having the transformation in your equation will undo that anyway, if you do that properly. All right, our R is -0.999072, and our R squared is 9981444. Okay, write this equation for the transform data. Okay, so the basic equation for a least squares regression line is EV equals A. Oh, sorry, EV, what am I doing? RV equals A plus or minus B EV, right? Now with my students, I just get them to write this as many times as it helps them be able to do this properly. So we have, I'm going to sub in my A value, 2 decimal places, so 256.22. And then I've got minus, remember to take the number in front, so minus 190.06, so 2 decimal places, that one's going to round. Now for RV, that was temperature, and I didn't do anything to temperature, so that's going to stay the same. So you can just write temp. And for our EV, that was time. However, remember I transformed that data. I no longer just have time, I have the log of time. If you omit the transformation out of your equation, you will not get full marks. You need to be transparent about what you have done to the data. Okay, so you've done a log of time. You also need that transformation in order to make accurate predictions. And I'll show you what I mean in a second. All right, so that's our equation. Now, also it's good practice if you are finding you're making mistakes with rounding, just make sure you have your values, full values somewhere. Like you can write them off to the side, like what I've done up here. So you can write your A and your B off to a side with lots of decimal places and label them, and then have a go at rounding, because then you potentially might not lose as many marks that way if you have made a mistake. So that's just a tip for you. Take it or leave it. All right, use this equation to predict to 1 decimal place the temperature of a piece of metal after 15 minutes, correct to 1 decimal place. Were we reading this in minutes? Yeah, cool. All right. So 15 minutes. So remember we've got the temp is equal to 256.22 minus 190.06 log of time. And it's always base 10 for general maths. Now, 15 minutes out of these two variables, I have the time, okay? So that just goes in like this, okay? And we use the CAS to do that for us. So going to our main page, we've got 256.22 minus 190.06 times, open up your keyboard, we want log 10, base 10, and we want 15. And that is 32.6 blah, 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 blah. 32.69. So 1 decimal place, so 32.7. And that's temp, so that's degrees Celsius. Now, if you have a look at our original data for 15 minutes, it is getting lower. So 15 minutes, I'd expect it to be probably around that 30 odd mark. All right, so that checks out. Whenever you're doing a prediction for for transform data, you can always refer back to the original table of values and just make sure that it fits in with your data. Because I'll show you what happens if I wasn't to put that as log of time, if I just did time, it would give us a ridiculous answer. So with the CAS calculator, remember it works like a computer, so you can just highlight it with your stylus, drop it down, and then you can edit it if you want to do something twice, like that. So if I don't have the transformation, I'm going to get negative 2,594 and 0.68, which is a temperature. So that is absolutely ridiculous. So that should be screaming in your face that you've made a mistake and you haven't got the transformation in there. If you've ever got a Y transformation, just use solve all the time. Now, if you're using a TI calculator, same thing, just use solve. It's heaps easier. Okay, so that is that one. This next one, again, so my temp is equal to 256.22 minus 190.06 times log 10 of time. The time that we expect the piece of metal to have cooled to 100 degrees Celsius. So this time we've got the temperature. So I've got 100 equals 256.22 minus 190.06 times log 10 of an unknown time, or x. So whenever you're finding something within the equation, you're going to use old mate solve. Now, hopefully you've got a shift key command set for this. My kids all use shift equals to bring up solve because it's really annoying having to find it all the time. We're going to go 100 equals 256.22 minus 190.06 times log base 10. A Casio calculator is programmed to find x, so I just let it equal x, and then I don't have to comma x at the end. I press execute, and that is my solution. So that is 6.637 minutes, 6.637, 6.637. If I go back to my original data, 100 is going to be a little bit lower there, around there, and what do you know? It's very close to 6. So the world makes sense again. That transformation, I've definitely put that in the right place. Correct to the nearest minute, so this is going to be approximately 7, because it definitely wouldn't have got to 100 at 6. We're going to have to round up. All right. Hopefully that has helped go through the process of transformations. Again, if you don't know how to do linear regressions and analysis, you would have been very lost in this process. So please go back and get your head around that first before looking at this. This is more for a SAC sort of process where you're making decisions and you're choosing something. In an exam, you'll be told, well, it's kind of similar to this, like you'll be told what transformation to do, and hopefully I'll post another one of these shortly just to do a Y transformation.